Today we're going to talk about inverse functions. We will start by reviewing some vocabulary and information about functions and how to identify them. It should be mostly review. And then we'll discuss what an inverse function is and how to find it, and we'll do some examples. Relations, they are pairs or ordered pairs. They're points, like when you would graph. Typically an x and a y value, they go together. The domain is of a relation are all the possible x's, and the range of a relation are all the possible y's or outputs. A function is a relation where each input has a single output. For example, in this case, whenever I put a 1 in, a 2 comes out, and only a 2. Whenever I put a 2 in, a 4 comes out, and only a 4. That's how I know this is a function. When you're given ordered pairs, to determine if the relation is a function, you can look to see if all the x's are unique. For example, in this first one, I've got 2, 4, 8, 10, and 4, 4. Is this a function? Yes or no? Yeah, all the x's are unique. This is a function. Look at the second one. I've got a 2, 5, a 2, 7, and a 3, 9. The 2's are repeated. In this case, when I put a 2 in, sometimes a 5 comes out, and when I put a 2 in, sometimes a 7 comes out. This is not a function. Below here I've got a mapping. When I put a 1 in, a 2 comes out. When I put a 4 in, a 5 comes out, but sometimes a negative 5 comes out. So this is not a function. And then in the second mapping on the bottom right, if I put a 1 in, a 2 comes out, a 2, a 4, a 3, a 10, and a 4, a 10. Now in this case you might be concerned about the fact that there's a couple of these that get repeated. Well, it's not a big deal if more than one x makes the same y. In this case, when I put a 1 in, a 2 comes out, and only a 2. And when I put a 5 in, a 2 comes out, and only a 2. So as long as whenever I put in a particular input, the same thing always comes out, then it's going to be a function. When you're looking at a graph, you can determine whether it's a function or not by using the vertical line test. If a vertical line only touches the graph once, then each point on the graph has an x that's unique. When the vertical line touches the graph at more than one point, then there are x values that result in 2 or more possible outcomes. In the second graph, let's say the dotted line is at x equals 3. If this is a 2, and this is a 4, and this is a 6, well, what happens here is that this point would be 3, 2, and this would be 3, 4, and this would be 3, 6. So you can see here how the vertical line test makes it really clear with a graph whether or not the x's are unique. In this case, this is not a function. So looking over here on the left-hand side, you'll see a variety of functions. This first one's a line, the next one's a quadratic, then we've got some kind of wavy line. These are all functions because they all pass the vertical line test. On the right, these are not functions. The vertical line test in each of these cases make it clear these are not functions. If you take a look at the third one on the bottom, you'll see how it doesn't always pass more than one point, but at some point at -3 it definitely passes more than one point. So this is not a function. This is function notation. Just a little review about this. We read this as f of x is equal to 2x, and the f doesn't stand for function, it's the name. For example, it could be g of x or h of x or k of x, but a lot of times we use f, and the x tells us in the parentheses, tells us what the input variable is, and then this other part we often call it the rule. That's what we actually do to the x or the input. The f of x is also known as the output or the y. We talked about functions being inputs and outputs. In this case, x is the input and f of x is the output. Here f of x is equal to 5x plus 3. And if I want to know what f of 1 is, basically what they're saying is, what is the output if I put a 1 as an input? In this case, it's going to be 5 plus 3, or 8. And again, you look at the poster at the bottom, I'm sure you've probably heard this f of x is the same thing as y. That's because y is the output. F of x is just the output. Here we've got an inverse function. An inverse function is simply a situation where the x's and the y's get reversed. You'll notice that when I put an a in, a 3 comes out. Well, in the inverse, when I put a 3 in, an a comes out. All these values have just been reversed. That's what an inverse function basically is. I bet you recall function machines from middle school. In the top example, we put apples in, and then the function changes it to an output of lemons. Well, if I take those lemons, the outputs of the original, and I put them as inputs into the inverse, apples are going to come back out. What happens is it just reverses it. Take a look down at the bottom here where we've got this function f of x and the ordered pairs 2, 9, 4, 5, and 11, 6. If it's inverse, all we do is switch the x's and y's, and you'll notice how the domain and the range switch around. The domain of the original function is going to be the range of the inverse function. Here are two functions. The one on the left is presented as a table of coordinates, and the one on the right is presented as a mapping. On your paper, write down the inverse for each. Pause the video and then check by starting back up again. Okay, hopefully you did that. And so here's the table where all we did was switch the x's and y's around. And then with the mapping, all we do is rewrite them with the x's and y's switched. And then the lines draw what happens to what. Here we've got a set of ordered pairs and their domain and range. On your paper, write down the inverse as ordered pairs, and then write down the inverse's domain and the range. Pause the video and then start back up again when you're ready. Alright, great. Hopefully you did that. You will see all you had to do was switch the x's and y's around to get the inverse. And you'll also notice that the domain of the original is the range of the inverse, and the range of the original is the domain of the inverse. And then this notation, f negative 1 of x, we would say the inverse f of x means the inverse of the function. The graph of a function is just a picture of all the x's and possible y's with the function. In this example, our function has only 3 points. In order to graph the inverse function, we simply reverse the x's and y's from the points and then graph them. Pause the video and try it on your own, and then start back up again to check. Okay, hopefully you did that. This is what it should look like. Now look at the graphs of the original and the inverse. Are they both functions? Decide and write down how you know. Pause the video and then start back up again when you're ready to check. Okay, hopefully you did that. The first one is obviously a function. It passes the vertical line test. The second one, the inverse, is not a function. It does not pass the vertical line test. This is not a function. A function has only one output for every value of x, as we discussed earlier. The outputs do not have to be unique. In other words, it's possible for more than one x inputs to result in a particular output. When this happens, we call it a many-to-one function. If a horizontal line touches more than one point on a graph, it's a many-to-one function. The inverse of a many-to-one function will not be a function. If a horizontal line only ever passes at most one point on the graph, we call it a one-to-one function. The inverse of a one-to-one function will also be a function. So we use this horizontal line test to look at a graph and decide whether its inverse will be a function or not. So let's look at this. Back to the example we just graphed. We determined that the original function on the left is a function using the vertical line test. However, note it does not pass the horizontal line test. That would tell us right from the get-go that its inverse will not be a function. You'll note here that the two y's that are 2's, well, when we switch them, they're going to become x, and then when they become x's, now I've got a non-function because I'm going to have two 2's as x values. Repeated x's are a clear sign that we're not looking at a function. Now in this one, what I've done is I've graphed and shown some points of a linear function. If you're given a graph with the points clearly labeled, or even if you can find the points yourself, it's pretty easy to find the inverse. All we've got to do is take these points and reverse them. So if I take 2, 3 and reverse it, it's going to become 3, 2. And if I take 1, 1 and reverse it, well, it's still going to be 1, 1. And if I take 0, -1 and reverse it, it'll be -1, 0. And if I take -2, -5 and reverse it, it'll become -5, -2. And once I've plotted those points, all I've got to do is connect them with a line, and that gives me my inverse. I can use the vertical line test and validate that both of them are functions, and they both are. Any linear function except for a horizontal line is going to pass the horizontal line test. So any linear function that's not horizontal is going to be a one-to-one function. Its inverse will be a function. And if I put in this y = x line, you'll see how the blue line is reflected over this line. For example, sometimes you may be given a graph and just asked if they're inverses. If they're obviously reflected over this line, that's a good indication that they are. In this case, I've graphed a few points of a quadratic, and if I take this and slide it using the vertical line test, I can clearly tell that it's a function because it passes the vertical line test, but it will not pass the horizontal line test. Here you'll see everywhere across this graph I'm going to run across two y's. Here's a clear one labeled 1, 1. And then here you'll notice the two 7's get repeated, but it happens over and over again. So obviously a quadratic, and I'm going to tell you right now, any quadratic's not going to pass the horizontal line test. Anytime you have a quadratic, then what's going to happen is its inverse will not be a function. What we're going to have to do is we're going to have to limit its domain in some way in order to make it so it is a function, and we'll talk about that later. If I'm given this and I want to graph the inverse, all I do is take the points and reverse them. So the inverse of 2, 7 is 7, 2, and the inverse of 1, 1 is 1, 1, and the inverse of 0, -1 is -1 and 0. The inverse of -1, 1 is 1, -1, and the inverse of -2, 7 is 7, -2. If I go ahead and graph this, now here I want to show you, this is going to come up later, you'll notice how I've got two parts. This is a square root function. Notice how the positive one, that's half of my inverse. And then when I do the negative square root function, you notice how it's going to go down. That's going to be the other half. This is what the inverse of a quadratic will look like. So the way we handle this is we would take the original, the quadratic, and what we would do is limit its domain. And so in this case, you'll notice the vertex, it's 0, -1. And so what I'm going to do is I'm going to change the domain here to where it is just all the x's are going to be bigger or equal to 0. Now when I do that, you'll notice that only half of the parabola shows up. This will pass the horizontal line test. If I were to take the inverse of just this part of my parabola, then the inverse will be a function. So what we'll talk about later is how we take a function and then limit its domain so it becomes a one-to-one function, and then we'll find its inverse using that. All I need now is this part of my inverse. Because I cut out half of the parabola, I'm only going to take half of the inverse. And these two are my inverse functions, and again, only because I've limited it. And then you'll notice that if I put in the y = x line, that it's also reflected over the y = x line. Okay, here are some things you should remember about inverse functions. The inverse of a function can be used to find the input of the original function when you're given the output, because we're basically just reversing everything. Inverse functions undo each other. We're going to use this f-1 notation to indicate that we've got an inverse function. If we are given, or we can find a set of coordinate pairs for a function, either in a table or a graph or some other way, all we've got to do is swap the values of the x's and y's, and we'll have the coordinate pairs for the inverse function. The inverse of a function might not also be a function. We're going to have to restrict the domain so the inverse is a function. And then lastly, if the graph of a function passes the horizontal line test, it's a one-to-one function, which means its inverse will also be a function. A quadratic is never going to be a one-to-one function. A quadratic's inverse will never be a function. We're always going to have to limit the domain in that case. Hope that makes sense. Thanks for watching.